In this video, we'll look at the idea of calculating work by integration. From physics, we know that work is equal to force times distance, but this formula is only valid when our force is constant. More generally, we could say the following. Work is the integral of force times distance. Where one of these two expressions involves the differential dx and where we've got appropriate limits of integration, so integrating from a to b. Here's an example. Find the work done in pumping water out of the top of a cylindrical tank 7 meters in radius and 10 meters in height, given that the tank is initially half full. Water weighs 9,800 newtons per cubic meter. Let's start by drawing a sketch. We've got a cylindrical tank. Let's put its dimensions on there. We know that the radius of the tank is 7 meters, and we know that the height of the tank 10 meters. We're also told that the tank is initially half full, so why don't we represent that in our sketch? Since the height of the tank is 10 meters, we know that the water initially has a height of 5 meters. Now I've drawn a second version of this cylindrical tank, and let's think about setting up our integration. So the key idea is going to be to imagine lifting a thin disk of water. We're going to be lifting it, pumping it out of the top of the tank. And so let's think about this distance here, this vertical distance that this thin disk is going to have to be lifted. Let's call that distance x. And so that distance there is going to be varying as we are pumping water out of the tank. Now in a moment we're going to need to think about the dimensions of this disk that we've just drawn. So we know the radius of the disk, but we'll also need to think about that tiny little height of the disk. And so that height there is going to be dx. That's because we're calling this vertical dimension here x. So a very thin slice across that dimension will have height dx. Next, let's think about our force, which is going to be measured in newtons. Well, we're told that water weighs 9,800 newtons per cubic meter. So if we multiply that by the volume of each very thin disk, then if we think about our units, we'd have newtons per cubic meter times cubic meters, which indeed would give us newtons. So working out the volume explicitly here, our force is going to be 9,800 times the area of that circular disk times its thickness or height, whichever word you prefer here. So let's look back at our disk. We're going to be able to find the circular area, and we're also going to think about that thickness or height, which is dx. So let's plug in here. Area, because we're talking about a circular area here, it's going to be pi times radius squared, so pi times 7 squared, and our thickness we've said is dx, and that's measured in newtons. So at this point we've got expressions for distance and force, and the last thing we need to do before setting up our integration is figuring out which x values we're going to be integrating through. So remember that x represents the distance that a slice of water has to be lifted. Initially our tank is half full, so at the beginning of the problem one of those very thin disks of water is going to have to be lifted 5 meters. Whereas by the end of the problem, when the tank is virtually empty, that thin disk of water is going to have to be lifted 10 meters. So we'll be integrating through the x values 5 to 10. So now we can refer to our general formula. Work is going to be the integral of force times distance. One of these two expressions, either force or distance, will involve a differential dx, and we'll make sure to put the appropriate limits of integration on there. So we'll be integrating from 5 to 10. Our force is 9,800 times pi times 7 squared dx, and I'm just going to put the dx at the back here so that when we then insert our formula for distance, which is x, so that this looks correct. We just want the differential at the end of the expression. So let's calculate our integral. We can move all the constants out in front of the integral. So 9,800 pi times 7 squared can come out in front, and we'll be multiplying that by the integral from 5 to 10 of x with respect to x. So now I'll recopy the constants. Doing our integration, we're getting x squared over 2, and we'll be evaluating that at 10 and then at 5. So now let's plug in. Plugging in 10, we've got 100 over 2, and then we'll be subtracting off the value at 5, which is going to give us 25 over 2. So putting this entire expression into our calculator then, I'll answer 5.7 times 10 to the 7 joules.